Welcome. In this session, we'll learn how to use Laplace transform to solve network analysis problems. Okay, let's start. So our goal is to learn how do we use Laplace transform to solve the network analysis problems. All right. Okay. So let's start. Hmm. So what are the steps involved in this technique? So in order to use Laplace transform to solve these network analysis problem, that there are three steps involved. Now, the first step that we do in Laplace transform using Laplace transform is we convert the circuit that is given to us into the Laplace transform domain. Now, how we do that? In the last session, we learned what happens to R, L, and C if we use Laplace transform domain. If we apply Laplace transform to these circuit elements, what happens to their voltage and currents? And we learned that in order to use Laplace transform, if we apply Laplace transform to these circuit elements, we know the resistor gets replaced by R in the Laplace transform domain. Similarly, if we apply Laplace transform to inductor, the voltage and currents in the inductor are this related by a quantity that's called SL. Okay, in other words, we replace inductor by simply LS in Laplace transform domain if the initial current stored in the inductor is 0. So if the initial condition of the inductor is 0, then we'll replace simply this inductor by LS or SL. Okay. Similarly, a capacitor in Laplace transform domain is replaced by 1 by SC if the initial voltage stored in the capacitor is 0. And same is true for the other elements like voltage sources, current sources, so we'll replace them by their appropriate Laplace transform models, right? So in order to convert a circuit into Laplace transform domain, we write the equivalent models of circuit elements, that is in resistor, inductor, and capacitor, and voltage sources and current sources that are given us to circuit. So we'll be writing the circuit. First step is writing the circuit in Laplace transform domain. Second step is find the equation that we need to find in the circuit. Find the equation of voltage, current that is needed in the circuit. We form the equation of that. Now, by using the appropriate circuit analysis techniques like KVL, KCL, mesh analysis, node analysis, or other terms that we have learned in the DC circuit. Now remember, this equation will be in the form of Laplace transform variable S. So we'll write the equation of that current or voltage that is needed. We'll write that in terms of S, right? That is the second step. Now the third step is once we have found the equation of the voltage or the current that we need to find in the circuit, we write the inverse Laplace transform of the equation that we have found in the second step. That will be our final solution or answer to this problem. For example, our goal is to find, if the goal is to find voltage or current, what we do, we find the equation of this voltage or current in S domain. Okay, then we find the inverse Laplace transform of that S domain voltage or current, and that will be our the V of t or I of t that we need to find in the circuit. So in order to learn this, understand these steps, what we'll do, let's take a very simple example. Let's consider we have an RL circuit, very simple RL circuit, where we need to find the current flowing in this RL circuit. Suppose we have an inductor and a resistor connected in series to a voltage source like this. Okay, suppose the voltage source is 3 U of t and inductance of this inductor is 2 Henry and resistance of this resistor is 4 ohm, and our goal is to find I of t. I of t. So this is the variable that we need to find in this circuit, and we'll assume that the initial current stored in the inductor are at the time of this at t equal to 0, the initial current in the inductor is 0. Means 0, the initial condition is in this circuit 0. So what we'll do, what is the first step? First step here is to convert the circuit into Laplace transform domain. So we'll replace this voltage source, inductor, and resistor by their equivalent models, right? So what happens to inductor in Laplace transform? We'll replace it by SL. Now the S is the Laplace transform and L is 2. So we'll replace it by 2S because the initial conditions are given here 0. So what happens to the resistor in Laplace transform? It will be replaced by R. So this resistor will be replaced by 4. Similarly, what will happen to the S 3 U of t voltage source? We'll replace it by 3 Laplace transform of u of t. What's the Laplace transform of u of t? Laplace transform of u of t is 1 by s. So let's draw the equivalent model of this circuit. Okay, so the equivalent of this will be, we'll replace it by inductor, like this. So what is the Laplace transform of 3 of 2? It will be 3 by s. Similarly, what's the Laplace transform of 2h? It will be simply 2s. And what is the Laplace transform of 4 ohm? It is 4. Now we'll write the current as I of. So this is the equivalent circuit of this in Laplace transform domain. Okay. Now once we have found the Laplace transform version of the circuit, what we'll do? We'll write the appropriate KVL and KCL that will give us the I of S, that will connect I of S in this equation. Now remember, once we have converted the inductor, resistor, and capacitor by their equivalent models, these equivalent versions are referred as impedances. Now, all the laws, techniques, and methods that we have learned for resistances are valid for impedances. Now, these are called impedances. 2S is the impedance offered by the inductor. 4 ohm is the impedance offered by the resistor here. Okay, these are referred as simply impedances of these elements. So all the techniques, laws, methods that we have learned for resistance are valid here. So what we'll do, we'll apply KVL to this circuit. So there are 3 elements. So we'll sum the 3 voltage drops to 0. So what we'll do, we'll apply KVL here. So apply KVL to this circuit. What we'll do, what we'll get. So what we have, we'll start from this point and move like this. So what we encounter first, we have a voltage source. The voltage of that element is 3 by S. And since we encounter the negative terminal first, so it will be 3 by S. Similarly, then we have an element. The impedance of that element is 2S and current flowing is I of S. So what will be the voltage drop? In 2S, the impedance multiplied by current is the voltage drop. So impedance is 2S, current is IS. So this is the voltage drop in inductor. Similarly, the voltage drop in this resistor is 4 multiplied by IS. Now impedance multiplied by current is again the voltage drop here. So sum of the 3 voltage drops is equal to 0. That's the KVL here. So let's simplify this equation now. Let's obtain this. Let's take this 3s on the right hand side. So we'll say R. Now it will be 2s plus 4 multiplied by IS is equal to 3 by. So 3 by S, I have written on the right hand side. So what will be I of S? So I of S here will be 3 divided by s into 2s plus 4. Okay, so this is our current. Okay, so this is our current. Okay, all right. Now next what we'll do, so since our goal is to find I of t, what we'll do, we'll find the inverse Laplace transform, this equation. So from this, if you know how to apply Laplace transform and inverse Laplace transform equation, the solution becomes very easy. So what we'll do, we'll try to find the inverse Laplace transform of this equation. So first, let's take this 2 common from this. So it will be 3 by 2 s into s plus 2. If I take 2 in count, so I can write this as 3 by 2 is 1.5 divided by s into s plus 2. Now, in order to find the inverse Laplace transform, since there are 2 factors in the denominator, what we'll do, we'll apply partial fraction expansion. So I can write I of s as 1.5. So I can write it as a divided by s plus b divided by s plus 2. So now to find this, so that's actually my 1.5 divided by s plus 2. So in order to find this a and b, what we'll do cross multiplication like this. Okay, so what we'll have to find a and b, what will be left, s plus 2 plus b into s will be equal to 1.5. Okay, so this is a step in order to find this a and b, the residues a and b. We multiply both sides by this denominator, or we do cross multiplication of this equation here. So once we multiply both sides by s into s plus 2, s and s will cancel. We'll have s plus 2. Similarly, when we multiply this s into s plus 2 to this term, s plus 2 and s plus 2 will cancel. There will be left with s. Okay. Now to find a and b, what we'll do, let me put. So to find a, let's put s equal to 0. So what we'll have here, a into 0 plus 2. This term is 0 is equal to 0.5. So a will be equal to 2. So that is 1 by 5 divided by 2. Okay, that is 0.75. Similarly, in order to find b, what we'll do, we'll put s is equal to minus 2. So a into this first term will be 0 plus b into b, that is equal to 1.5. So b will be equal to minus 0.75 because 1.5 divided by 2 is 0.75. Now substitute the value of a and b back here. What we'll get is as? So is will be equal to 0.75 divided by s plus b is minus 0.75 will be 0.75 divided by s plus 2. Now we know the inverse Laplace transform of 1 by s and inverse Laplace transform of 1 by s plus 2. So let's write we first take 0.75 common. So we are left with 1 by s minus 1 divided by s plus 2. And we know the inverse Laplace transform of these terms, 1 by s and 1 by s plus 2. So we can write taking inverse Laplace transform. Inverse Laplace transform, we have I of t. What will be the inverse Laplace transform of I of s? Will be I of t will be equal to 0.75. The inverse Laplace transform of 1 by s is u of t minus inverse Laplace transform of 1 by s plus 2 is e to the power of minus 2t u of t. So we can take u of t common. we can write I of t as 0.75 1 minus e to the power of minus 2t, u of t will take common. So this is the current that we needed to find in this circuit. So this is our current. Okay, so that's what we needed to find. So let me repeat the procedure again. First of all, our goal, we are given this circuit and our goal is to find I of t. So what we do, we convert this circuit in the equivalent Laplace transform version, that this is the equivalent Laplace transform of this. Then we apply KVL such that that connects this I of s in this circuit. This is the KVL. Once we have obtained the equation of I of s, we need to find its inverse Laplace transform. Now, from this onwards, this has nothing to do with in this network analysis. This is from the Laplace transform. If you know how to apply it in Laplace transform, inverse Laplace transform, you will be able to solve this equation. Now you can see the steps that I have done. This is called the partial fraction expansion method. I have applied that to find these coefficients, etc. And we arrived at this equation. Now we need to apply the inverse Laplace transform of this equation in order to find. So this is our answer. Suppose similarly, we needed to find the voltage across the inductor here. Suppose our goal here is now to find the voltage across this inductor. Suppose we also needed to find the voltage V of t. What is the voltage? Okay. Now, if I write the equivalent of voltage V of t, I can write as V of s. So this is the now remember all the technique. Once you have converted the circuit into the Laplace transform version, all the methods that are valid for resistance are valid for impedances now. Okay, now 2s of this inductor is simply the impedance offered by the inductor. So how is Vs and Is related? Vs and Is are simply related by the KVA. There's Ohm's law. We know voltage across impedance is I times Z. Now if you look at this, where Z is 2s, where Z for this element is 2s, and the current flowing is Is. So how do I write V of s in terms of I of s? So I'll say from this, I can write V of s is I we have written as I of s, Z is 2 of s. Okay. Now we already know what's I of s here. I of s is this. So if I apply it here, so we can say V of s. Let me use this equation instead of this. Let me use this one. Okay, such that s and s cancel. So let me use this. So this will be V of s will be equal to I of s is 1.5 divided by s into s plus 2 multiplied by 2s. Now s and s cancels, and 1.5 multiplied by 2 is 3 divided by s plus 2. So what is the voltage? So voltage V of s is 3 divided by s plus 2. Okay. So we know the inverse Laplace. We don't need to do the partial fraction because there is only one term here. We don't need to find the partial fraction expansion of this term. We can simply apply the inverse Laplace transform. So apply inverse Laplace transform here. So we'll have, what is the inverse Laplace transform? V of s, V of t will be simply equal to 3 into e to the power of minus 2t u of t. So this is the voltage across the inductor. This is the voltage across the inductor. Similarly, we can find the other term. Once we have found the current in this circuit in terms of the Laplace transform S, we can find any quantity in the circuit. We can also find the voltage across this resistor, right? Simply applying the Ohm's law. Remember, Ohm's law, this is called the Ohm's law for impedance. This is referred as Ohm's law for impedance. current voltage across the element is current multiplied by impedance. Now impedance offered by this inductor is 2s multiplied by the current. Now current we already know current is equal to this, like this. Okay. So this is how we find other parameters in the circuit. We could have also used directly this equation to find V of t. How? We know the voltage V of t in inductor is related to I of t. Since we have already found here I of t is already found here, we can directly use this. We know what is the relationship between voltage and current in time domain. In inductor is V of t is simply L dit by dt. And I of t is here. We can apply this differentiation to this equation directly and find the. Okay, so we can also use this once we have found I of t. But what's the difference? Since you need to do differentiation here, so you must know how to apply differentiation to this equation like this. See, the beauty of Laplace transform is it converts the integral differential equation. Means integral equation is a differentiation equation. It converts them to a mere algebraic equation. You can see here where these are algebraic equation. As you can check it, this is simply an algebraic equation, but the variable only here is s. Okay, that's the advantage of using Laplace transform. I hope you understood. So what are the steps? Let me repeat it again. First, we convert the given circuit, we convert it into the Laplace transform version. Then we write the appropriate KVL, KCL that will connect to the variable that we need to find in the S domain. Once we have found the equation, we need to apply the inverse Laplace transform of that. Now to do the inverse Laplace transform of this equation, we need to apply some method in this Laplace transform that's called the partial fraction expansion step that we have done here. Partial fraction expansion done here. Now to find A and B, we have done some manipulation here. Now once we have found A and B, we apply the inverse Laplace transform and we found the current. This is our current. Okay, and we can also find the other variables. So let me stop it here. In the next section, what we'll do, we'll say the currents, the initial current in the inductor is not zero. Okay, let me stop it here.